Okay, so let's see the next machine learning model, which is a famous classification model, K nearest neighbor classification. In a single sentence, nearest neighbor classifiers are defined by the characteristics of classifying unlabeled examples by assigning them the class of the most similar labeled examples. Despite the simplicity of this idea, nearest neighbor methods are extremely powerful. See, one thing I would like to point that almost 1/3 of classification problem uses KNN. Yeah, this is true. KNN is extremely powerful, and though it's simple, but it almost solve 1/3 of the classification problems. Concept which is used here is simple Euclidean distance. If the feature vectors are not normalized, normalize them, as it may lead to undue influence of some features which have high values as compared to some features which have low values. You will understand this. I'll explain to you in the next section. This is a simple, like, if you this is just to clear about what KNN does actually. See, if you have some like fruits and some vegetables and some proteins in this order, like grape, green bean, nuts and orange, and these are the classes. These are things, but these are classes. Like grape and orange are like fruit, green beans are vegetable, and nuts is a different class of protein. So see, these are the classes. So these are like measured on scale of two features. First is sweetness and second is crunchiness. So like grape is given 8 and 5, 3, 7, 3, 6, 7, 3. So what it does, Canon, it just like using K means we have a model already built. So Canon, what it does, like if you are given a tomato which has sweetness is 6 and crunchiness is 4, what it does, you have a group of points, like this is vegetable, this is like fruit, and this is protein. So like say tomato is here, so how can you say it belongs to either of these groups? So like it's given 6 and 4. So what it does, it measures each it measures its distance with each cluster. Like here it measured 6 with grape, it's measured 6 minus 8 whole square, 4 minus 5 whole square, and its distance is 2.2 Euclidean distance. Like say this is fruit section, so it measures and its distance is 2.2. Next it measures with vegetable, 6 minus 3, 4 minus 7, so the distance is 4.2. Say this is the vegetable section. Next it measures nuts, it's 3.6, so it's 3.6. So in orange it measures 6 minus 7 and 1.4, so here it is 1.4, because this is a fruit cluster, this is a protein cluster, and this is a vegetable cluster. So what KNN does is, like depending on the K, here if say we say K is equals to 1, means it takes only the one nearest neighbor, which is the nearest neighbor among these, like this is 1.4 orange, so it will classify tomato as a fruit because the least is 1.4. If say we say K is equals to 2, then it sees the nearest two neighbors, and based on the majority it classifies. Like for example, it takes 1.4 and what is the minimum, 2.2. So if this is a fruit, this is a fruit, so obviously it will be again classified as a fruit. But if say there's a different, like this is this is like 6.2 or something, and like the second most smallest is 3.6, this is protein and fruit. So based on these two and the smallest distance, let's say this is also in, here this is the smallest thing, so we'll say 1.4, so we'll say that this belongs to fruit. But for example, like say this is 1.4 and this is 2.2, so see 1.4, 1.4 and 2.2. So this is a fruit, this is a fruit, and this is a protein. So these two have same Euclidean distance. So based on the majority, like K is equals to 3, if we say K is equals to 3, so based on the majority 2.2, 1.4 and 1.4, so majority goes to fruit, so tomato is assigned to fruit, despite the fact that protein also has a distance of 1.4. Okay, so why Canon is lazy? Canon is lazy because it actually neglects the fact of learning a model. As I said earlier that there were the 3 steps involved. First is gathering the data, second is like abstraction, and then is generalization. Here in Canon there is no abstraction. We just push the data in the algorithm and just get the result out. So that's why Canon is instance based learning, means it just sees the data and based on the Euclidean distances only classifies the data. Yeah, and how to choose K? K is just simply run your data set several times with different Ks and see which K is best for you, like which is giving the minimum error. Let's see how. This exercise I am gonna start with is like I'll use the iris dataset. This iris dataset has like 4 features: sepal length, sepal width, petal length, and petal width. And this is category species. Species, this has 3 categories. Like this has 3 categories like Setosa, Virginica, and another category. So let's see the code. What I have done, I have called the 3 libraries, 3 packages actually: class, gmodels, and psych. Psych is actually used for that plot things. And I have loaded the iris dataset. str is simply to see the structure of iris dataset. Summary iris will summarize the result for you, like it will show the median, quantiles, and all for numeric data types, and the categorical and level variables for species data. So I have here I have used a statement table iris dollar species. What it will do, it will in a tabular form it will show all the results, like what are the number of entities in all the 3 categories table wise. And here this is an important thing, like, and if you will see that this data set, if you'll see in the R Studio, this data set is not sorted actually. This is actually sorted, but to like your data set should be like distributive. It should contain each observation in a distributive manner, like it should not contain a cluster of Setosa only, like, because if it contains a cluster of this species only, then how will be you sure that it will correctly predict another category? So you should actually randomize your data set. So that's why I have written this code of randomizing this data set. This is nothing but just a function created. What it does, it accepts a data frame and seed is equals to null. Seed, what does seed does is it actually recreates the randomized, like if for one instance 1 2 3 4 is created, another for the second time also it will recreate it. So in this what it does is like it will count all the rows of n row data frame. Like what n row does is like it calculates total number of rows in the data frame. Here the data frame is iris, so it will calculate all the rows and store in this result n row data frame. And what this expression does is like it creates a vector from 1 to total number of rows and pass it to index. So in all, index will contains total number of rows from like in the order 1 2 3 4 and all. And what train index and train set is does, like you have a data set. So what you want to do is divide your data set into training data set and testing data set. So that's why I am creating a training data set and a test data set. So what test data set should be, like how much size your test data should be, and how much training data set your how much train set your training data should be, depends on the size. So try taking 3 by 4 and 1 by 4 because the more the amount of data you train, the better the accuracy of the result you will get. So and that's what I'm doing here. I have created the total index, and out of this index I'm sampling the 3 by 4th. I'm sampling not 3 by 4, I'm here sampling 4 by 5th, because the more the data you train into the model, the better the accuracy you get. So I'm getting the train index in these my sampling. This will be like 44, 58, 67, 120, 131 and all these. And the train, I have created the train set using data frame train index comma this, and test is like minus train index. Here minus is like omitting all these indexes which have already occurred in train dataset. So test set is all those indexes which have not occurred in train set. This train set and test set I have returned as in the form of list, and this is the function. And now I'm using pairs.panel iris just to see the relationship and correlation, and just visualizing the data. One more thing, why I have written a normalize function. What normalize function does is, like in KNN and also in other algorithms, like you can see here the data is like in 5.4, like 3.5 and 1.3, and on the other hand like 0.2, 0.3, 0.4. So what KNN does is like it measures the Euclidean distance. So what if some vectors like here and here, this has like a smaller amplitude, this is higher amplitude, so this vector will have much more dominance as compared to this. Like in the equation, like sqrt 6 minus 8, this, like if you say 5.1 minus 4.3 square, this will have more dominance in addition as compared to this smaller amplitude vectors. So to nullify this concept, we have to just normalize this, because then only it will give correct Euclidean distances. That's why I have normalized this using a normalize function. Concept is similar. I'll return x minus min of x upon max minus min. This will just return the total amplitude value, and I have minimized the minimum of x, and this will return in the 0 and 1 range. So what I have done, these are the two functions defined. Now what I'll do, I'll split the iris dataset into train and test dataset and return the result in splits. This will be a list type. By running this command, you'll be able to see. Then I am just observing what splits will contain. L'apply splits head will just show the first rows of splits, like in splits is a list, so for train and test data it will show the first 6 rows, and for this function enrow also L'apply will return the number of rows in the train set and the test set. Then what I am doing is, I am storing the iris train. I am storing the iris train data set. Like I have returned a list, so I'll store the iris train data set in a iris train label, because list this is a list. It will split, it will have two sections. First is train and second is test. So to store the train dataset, I'll use the splits square bracket 1 and convert it as a s.data.frame, because initially it is in the list class. So and then I'm initialize in iris train label, and then I'll see the this is command just to observe. Like you have to get hands on these commands, because these will really be helpful for you. So then again for iris test, I am using as.data.frame splits 2. Then what I am doing is, like I am normalizing these data sets, and the concept which I have explained earlier, I am using L'apply once again and normalizing this from iris train 1 to 4, because only 1 to 4 I am concerned with. The fifth column is like a species column, so from 1 to 4 I'll normalize the data set. And then I'm just printing, and I'm just assigning iris train labels in iris train, means I'm assigning all the rows with the fifth column, means which is the species column, in the iris train labels. And similarly for iris test labels, I'm seeing the structure and summary. Okay, then simply I am using iris predicted, means I am just passing the train is for like you can see here the syntax train, test and class. It just simply uses the function. There is no as such model obtained, just it needs a training data, test data, and class and number of cluster number of nearest neighbors you want to assess. So it takes a training data, a test data, and class which you want to assess. And I have taken here nearest neighbors 9, because for this only I have got the 100% accuracy. Like you will use these, and for assessing the accuracy I have used a cross table. What it does is, like, it shows the result in the form of this table. Like I have predicted this, and I have the iris test labels. How did I obtain these iris test labels? Is using this iris test labels. Is earlier I have stored the results, and after prediction and storing iris predicted, I'll compare this test labels and this predicted using a table. So here I have used this cross table, and I have obtained setosa and setosa, all the 7 observations. Similarly for versicolor and virginica. So as you can see, I have not got any false positive or false negatives, like no errors. So this is 100% accurate. One thing I want to tell, that not all of the data set will give 100% accuracy. If you are getting 68% or 70% accuracy, actually that's very good. Why I am getting 100%? Because it's solely made for KNN, and this is an ideal data set, and it's very famous for learning purposes. So don't get sad why I am not getting like 90% or 98% accuracy, because even 68% is very good. And like this in the program also I have pairs plot. This pairs.panels iris, this graph is this thing. So what it does, it shows the various correlations and various relationship between various features of this dataset, like sepal and sepal width in various histograms and curves. Like this is like normalized, and this is like here. What does this ellipse signify? Ellipse signifies the relationship between these things. Like more the stretch the ellipse, the more the correlation between these features will be. Like here you can see in these two, like petal length and petal width, the ellipse is very stretched, and you can see the correlation is actually tending to 1. So you can say these are very much correlated. And what is this circle ellipse? Actually this is nothing but top view of a Gaussian distribution, and this red dot here is nothing but the mean of this curve. And these are like simple scatter plot, and these are the histograms. And just look at the data set and assess from it, take out the inference, what actually does the data set signify. And this was the simple introduction to KNN. And next we are gonna look onto the naive Bayes classification, which is also very famous.